All right, so today we're going to cover states of matter. Specifically, this one will cover what we call kinetic molecular theory. But let's start about states of matter. So I'm going to fill out this little chart here. So a solid, its volume is definite. So it's a definite volume. Liquid is definite. Now, it has an indefinite shape, but it has a definite volume, meaning its shape is, it doesn't have a definite shape, meaning if you pour it out, it's not going to really take a shape. It takes the shape of its container. But there's definitely a volume. And the reason why it has a volume is because in a liquid, the molecules are in contact with each other. They're just kind of sliding or moving past each other. And then a gas has an indefinite volume. And you guys actually did this because if you remember the syringes, you were able to take the syringes and push or change the volume even though you had the same amount of gas in there. When it comes to molecular motion, solids are going to be your lowest or slowest. The molecules are actually not even moving, they're just vibrating in place. They're very ordered. And then the molecular motion, this would be medium, I guess, or they're moving, but they're still in contact with each other. And then gas is the fastest. And then this would be dense, not very dense, or I don't know. What would you put, like medium density? And then low density. So we can say, let's put high density here. Okay? All right, so that's your states of matter. Okay, so we're going to talk about gases. So the state of matter that we're going to discuss is gases. And so when we talk about gases, we're going to talk about the kinetic molecular theory, also known as KMT. And there's three major parts to the kinetic molecular theory. One is particle size, particle motion, and particle energy. So particle size, so gas particles are tiny, and they are separated from each other by great distances. In fact, the distances between the particles are a lot larger than the particles themselves. And because they're so far apart, they're not attracted to each other. There's no attractive forces, like the magnetic positive, negative forces. And then, so therefore, since they're so far apart, they're mostly composed of empty space. So it's really, really low density. They're not closely packed together. And remember when you did the syringe and you're with the liquid, since it's more closely packed, you're not able to compress the syringe. But you were able to compress the syringe considerably when you used gas, right? Or when you had gas. So here we have a guy looking like he's going to jump into a pool, right? The reason why he's able to fly through the air is because it's less dense. And then when he hits the water, he'll be able to go through that because there's some density to it, but there's some space that allows his body to travel through. But if you're going through the cement, he couldn't go through the cement. Yeah. Why? Because it's so dense. Great. Particle motion. So if you look, we can come up with some like guesses of what's going on here. But if you look at this, they're random motion, and they're always going in a straight line until they collide with each other. When they collide with each other, they bounce off. These collisions, our energy is transferred in these collisions but not lost, and so we call this elastic collision. So an elastic collision is when no energy is lost. So when it comes to particle energy, so we just talked about how they transfer energy. One thing is temperature is the measurement of kinetic energy, and so the higher the temperature, the greater the energy released there. So two factors determine the amount of energy. One is mass and one is velocity. So the greater the mass, the greater the mass, the greater the amount of energy, and the greater the velocity, the greater amount of energy. But another way to think about it is mass and velocity are indirectly related. But by the way, if you look at this equation, you'll notice that which one's more important in terms of energy. mass or velocity? Well, take a look. Velocity is squared, which means its value is even more important. So that's why, like, say, a bullet traveling at a high velocity with a low mass will cause more damage or have greater energy than a bowling ball traveling at a lower velocity, right? Because actually velocity is more important when it comes to energy. Oops. All right. Mass and velocity are indirectly related. So if you think about it, if the energy is the same, but the mass goes up, the velocity will decrease. And then conversely, if the mass goes down, the velocity will increase. So therefore, a smaller gas particle will move faster than a larger one. So if we take a look here, if I open up 2 vials of gas, which will you smell first, chlorine or ammonia? What do you guys think? Well, the answer is ammonia. Why ammonia? If you determine the molar mass of ammonia, it's 17.03, and then chlorine is 70. So 17 versus 70, ammonia is smaller, and so therefore will move faster to your nose. All right, how does it move? Well, it moves through diffusion. So diffusion is the movement of a material through another material, and this happens until it's equally distributed. So you did this in station 1, where you noticed that the hot water, because the molecules move a lot faster, it allows the dye to diffuse quickly. But once the dye is all spread out equally, it stops moving, right? The rate of diffusion depends on particle size and temperature. Bigger particles tend to move slower, and so the diffusion is slower. And then remember temperature. If you're hotter, the hotter it is, the faster it diffuses. Why? Because the particles themselves move faster. Effusion is just the ability of a gas particle to escape through a tiny opening. So you actually did this when you smelled those 4 balloons. Some of them you smelled and some of them you didn't. Like water, you're not able to smell. Why? Because its effusion is very low. But then some of the other particles, like the vanilla extract or the lemon extract, its effusion is a lot greater, and so the molecules inside the balloon were able to escape. So then it reaches your nose, and you're able to smell something. Okay. All right. There is a formula called Graham's law of diffusion. It looks at the relationship between the rate of travel and the mass of the particle. But you should already kind of know, like, the bigger the particle, the slower it's going to go. So this is a way to actually determine the ratio or rate of travel or velocity between 2 particles. So let's do an example together. It says ammonia has so let's go ahead and write down. So remember, it's V1 over V2 is equal to the square root of M2 over M1. So they're opposites of each other. Let's go ahead and write it down. So equals the square root of M2 over M1. Now, to make it easier for you, my suggestion is always make particle 2. So V2 or M2, you always want, M is the mass, by the way, you always want it to be the bigger particle. It'll help you. And then so V1 and M1 will be the smaller particle. And I mean smaller by size or mass. So so if I plug this in, V1 over V2 equals, so ammonia is 17. So the bigger particle is hydrogen chloride, so I'll put that there. And then ammonia is smaller. So it says ammonia is sodium chloride is 36.5, right? So 36.5 grams per mole over, and then the bigger particle is I'm sorry, the smaller particle, V1, is 17.0 grams, right? And so if you take 36.5 divided by 17, let's do that. So 36.5 divided by 17 is about 2.14. So the square root of 2.14 is V1 over V2. So this, I think it was like 1.49 or something like that, right? And so what this means is that your V1, so NH3 moves let's say 1.5 times faster than HCl. Why? Because if we compare V1 to V2, it's 1.49. So V1, which is our smaller particle, NH3, will move 1.5 times faster than HCl. Okay, so let's try this one, which has a greater effusion rate, carbon dioxide or hydrogen gas. So carbon dioxide, its molar mass is around 44.01 grams per mole, whereas hydrogen gas is going to be 2.02 grams per mole. And so remember, we want to make, so this will be our 1, and this will be, we want to make our bigger one 2, and then this will be particle 1. So this is going to be my mass of 2, mass of 1, so V1 over V2 equals the square root of M2 over M1. So this equals 44.01 divided by 2.02. Take the square root of that, so 44.01 divided by 2.02 is 21.787. And I'm going to take the square root of that. Let's try that. So let me find my square roots. 21. Let's do this. So 44.01 divided by 2.02. Take the square root of that. So it equals about 4.67. So H2 is 4.67 times faster than CO2. Okay, so you can kind of figure out. Now, so you can see how many times faster comparatively. All right, and so you got an Ed puzzle on kinetic molecular theory.